Welcome back to ECE 441A, 541A. If you are familiar with the concept of engineer's breakfast, the college actually has a breakfast on homecoming weekend on that Friday. And if you've really been paying attention to your course syllabus, you realize that we don't have class that morning. That's a Friday morning. You can go ahead and go to the breakfast. It's free for those seniors that are graduating this year, meaning in December or May or even August of 2015. But you do need to RSVP if you're interested in going. So if you're used to getting up, you can go to the breakfast if you're a graduating senior, compliments of the college, but make sure and find the right email and the link to RSVP. That's one of the announcements. The other one is that homework number 3 is due today, and hopefully there is a Dropbox on D2L for that. Today what I want to talk about, continue with this idea of sensitivity and how feedback actually plays a key role in minimizing or adjusting the sensitivity. And the sensitivity is a way of measuring or keeping track of how a parameter change may impact a particular transfer function. We'll define two different functions, a sensitivity function and a complementary sensitivity function, and those actually both sum up to equal 1. And if you raise one, then you lower the other, or there's this trade-off, and that's what I want you to understand. Engineering in general is a big play on trade-offs. Control theory is one of those areas where you see trade-off a lot. And we'll see trade-off in this class in particular with transient behavior and steady-state accuracy or steady-state error. You sometimes have to trade one of those off with the other, and a lot of times there's a nice compromise. You can achieve a nice steady-state accuracy and an acceptable transient behavior. We'll calculate then a sensitivity. Let's say the sensitivity of a closed-loop transfer function t to a particular parameter alpha. We'll just work through an example. Then I will give you, or we may actually, in a way, derive a new sensitivity formula that sometimes is easier to play with than the sensitivity formula that we derived last time. If we have time, we will start sketching Bode plots, because I know you guys have this Bode plot right here and you just want to sketch it mentally. And we'll look at this sensitivity expression, which is a function of the complex frequency variable s. That means it's dependent on frequency in general, and it would be nice to maybe know if this parameter varies, how is that maybe going to be influencing the system behavior at various frequencies. And the sensitivity function, if you sketch its magnitude Bode plot, you can see which frequency intervals or regions might be more sensitive to this parameter variation than others. Meaning if this parameter changes, if we're now operating or worried about the behavior of this system in certain frequency ranges, we may have a bigger impact when that parameter changes versus others. As a heads up, I don't think we'll get there, but we will start getting into Chapter 5, which is design specifications. We'll translate time domain behaviors that we might find desirable. For example, we might have a particular overshoot that we're interested in, or maybe a particular rise time, or a particular settling time. We will translate those actually into regions in the complex S-plane where we want our dominant poles to live. That's where we're headed. To get started, I need to actually correct this diagram, because in the book this is labeled E sub A, and it's actually important to make the distinction between the signal coming out of that leading summing junction and what typically is used in the textbook and maybe elsewhere is E, which is a tracking error, which is the reference signal R of S minus the output Y of S. This is now the tracking error, and that's not the same as E sub A. It would be if that noise input, that's maybe sensor noise. You might have some noise coming into your sensor. That's what N represents. T sub D might be a disturbance. Let's say you're out in your yacht, and you now have a constant wind coming at you in some direction. That might be considered a disturbance. Or let's say you're driving and you've got your cruise control on. It was set when you were just driving across Kansas, which maybe if you don't know your geography, Kansas is pretty flat. And then you hit a hill. Maybe you get into Oklahoma or something and you start going up hills. Well, that's now considered like a disturbance, that change in incline. That would be like T sub D here. That wind hitting you in your yacht from maybe an inappropriate angle, or from a direction that you would prefer to maybe minimize that impact of the disturbance. We have our controller, G sub C. We may have some sensor dynamics, H, and we have our plant, G. You have a plant in the lab that's this mass spring damper system. When you see that G, just start thinking of your plant in the lab, shaking and telling it what to do or how to behave. This is now the block diagram that is important in thinking about control problems in general, because a lot of times we get too narrowly focused and we only worry about the transfer function between the reference signal R and the output Y. But keep in mind there's possibly other inputs that influence the output Y and consequently influence your tracking error. The difference may be between where you're wanting to go and where you're actually going. Usually you want to minimize or keep that tracking error small. If we have 3 inputs and let's say 1 output Y, how many transfer functions do we have? If we consider a transfer function between each of these external inputs, a reference input, a disturbance input, and a measurement noise type input, then you could have 3 different transfer functions. One between the reference input and the output Y, one between the disturbance, T sub D and Y, and another one between the noise and Y. Now we have 3 different transfer functions. The textbook actually goes ahead and sets the sensor dynamics to 1, just to make things a little easier, and they collapse the product of G sub C and G, and a lot of times you'll see books, in the other book for this class, you might have a loop gain of all the transfer functions in your loop, and that might be L equal to G sub C, G, and H. The book now sets H equal to 1 in chapter 4 to help simplify some of the analysis, but you may see L appearing. Well, that's just now this product of G sub C and G. That's what we'll call the loop gain. That's the gain in the entire loop. That's the combination of the plant and controller. If you then do your block diagram algebra or your Mason's gain, you can come up with a transfer function, or these 3 transfer functions between your reference input, your disturbance signal, and your noise signal, and this tracking error E. That's not E sub A, that's E now. E is R minus Y. And I've labeled some of these, but I've collapsed the product of G sub C and G down into just one variable, which I'm calling L, the loop gain. This first transfer function should look very familiar. You should feel warm and fuzzy when you see that. That's 1 over 1 plus L. Or if you had G and H in there from last time, it was 1 over 1 plus GH. That's the transfer function between the reference input R and the air signal E. I've now defined S and C because S is, in the control literature, referred to as the sensitivity function. And that's equation 4.5 in the textbook. And again, L is the loop gain, but now I've labeled this C up above, and C is actually called the complementary sensitivity function. And the reason that's called that is because it's complementary to S. If you simply looked at adding C plus S, you'll get 1. It means if you try to reduce S, what happens to C? So at different frequencies, S is a function of frequency. Let's say S is 1/2. What's C at a particular frequency? Checking to make sure we're all awake on what is today? Wednesday morning. C would be 1/2, wouldn't it? I greeted you with a very challenging addition problem. 1/2 plus 1/2 is equal to 1. But now if S goes up, or if you try to reduce S, let's say you try to drive S down to 1/4, remember what S is associated with? That reduces the impact of a parameter change on your transfer function. So you may want to minimize S. Now S is 1/4. What's C? 3/4. This is very challenging algebra, isn't it? But what that's telling us is sometimes these adjustments in the frequency are called the waterbed effect. Maybe that's an old terminology. Maybe you don't worry about waterbeds anymore. But if you push down somewhere on a waterbed, it sort of tends to go up somewhere else. And that's this relationship between S and C. Here, if we reduced S, now what's going to happen between our air signal and the noise? Noise now might have more influence on the air than it did before. There's this trade-off. But maybe you know something about your noise characteristics, and maybe you can play that. Maybe it's only noisy in certain frequency intervals. So there's a lot going on here, or can go on here, and that's why you'll get paid the big bucks to try to understand this stuff. Right? There's a lot going on. It may not just be as simple as what it sometimes seems. Oh, I just have to put my poles in these locations in the complex S-plane. Well, I've got 3 transfer functions to worry about: the noise, the disturbance, and the reference. But that's this relationship between S and C and this trade-off issue, the waterbed effect, where if you decrease S, you may increase C, and that's going to then influence how you shape your frequency response. And that's the whole point of this G sub C, is to modify this Bode plot, or the frequency response of your system. That's why you're designing this controller. Questions on this relationship or this concept? You have a block diagram. That block diagram now you've seen depends on R, T sub D, and N. So there's 3 different signals coming in to impact that. If you play with one, you may have to worry about what's happening with respect to the others. That's what I'm wanting you to be aware of today. Now that we've sort of gone over that material, let's actually look at where we left off last time. Let's look at a particular example of applying what we talked about last time. Suppose that you now are given the following system. Maybe a G1, I'm not even going to call it a controller, I'm just going to break this up into two different transfer functions. What is that? If somebody said, describe what's happening in that block, what are you seeing or thinking? Pardon? That is something, if you looked at its impulse response in the time domain, would have an exponential decay. It's first order, isn't it? First order. That's like a low-pass filter, a first order low-pass filter. That's just a pole at minus alpha. And alpha is going to be our adjustable parameter in this discussion. Then let's say that we have a second block that's given by 1 over s plus 1. So here is G1 and G2. Those would all be the same if alpha was 1, right? You would have two similar looking low-pass filters cascaded together. You've now chained these low-pass filters together. If you remember your 320, that may or may not be what you want to do if you're just filtering. You may want to design your filter. Oh boy, I must be hungry. Speaking of Kansas, what did we talk about when we were designing filters, and maybe the trade-off or the alternative to just ganging these low-pass filters, 1 over s plus 1, another one 1 over s plus 1, another one 1 over s plus 1, just throwing all your poles at minus 1 may not be the best location. If Kansas is flat and you have you might want a Butterworth filter, right? We were talking about pancakes, flat as a pancake, Kansas, Butterworth filters or Butterworth syrup on those pancakes. And did you see the current event somewhere, either this weekend or this week? Butterworth is wanting, never mind, there's a lawsuit involving Butterworth syrup and Butterworth. Where did that come from? I don't know, but it's morning. Speaking of the engineer's breakfast, they might actually have pancakes. Okay? And you can just start talking about Bodie plots at your table and impressing the alumni and maybe the industry reps that are there at the engineer's breakfast, talking about filtering and how you might design those. So you might want to place those poles in a Butterworth pattern, which are not just all on top of each other. Well, let's put some feedback in here. Here's our reference signal, R of S. And now we can just call this E because the tracking error and that location is the same because I'm not considering a noise, any sensor noise. I'm neglecting that. Here is our system. What's the closed loop transfer function of that system? If I said, what's the ratio involved to find that transfer function, what would that be? Man, you guys are on top of it. Did you hear that? But I was expecting first to just say, well, that's Y of S over R of S. I figured you'd be looking for partial credit. So you say, oh, the transfer function between the input reference and the output, and then that's just G1, G2 over 1 plus G1, G2. And that should just be coming to you automatically now at this point in the semester. That's G over 1 plus GH. H is 1, and G is this product or cascade of G1 and G2. That's our transfer function. In this particular case, if we insert the specific parameterized forms of G1 and G2, G1 was 1 over S plus alpha, G sub 2 was 1 over S plus 1, all over 1 plus, wait a minute, I can't even follow my own notes. I wanted for G1, I wanted to put a gain in there. Can you accept that? Now all you have to do is add 2 lines to that. So now you have K over S plus alpha. I now want that down here to be K over S plus alpha, and then I have K over S plus alpha 1 over S plus 1. I got so excited about talking about low-pass filters and pancakes, forgot my gain K. Okay. Now, what's the ratio of polynomials here? If you put everything over a common denominator, which is S plus alpha times the quantity S plus 1, the numerator you don't have to worry about. That's just K. And in the denominator, you just have to worry about that product over itself to create 1, cancel the common denominator, and you end up with K over S plus alpha, S plus 1 plus K. That's now our transfer function, and we want to know what's the sensitivity of that transfer function. It's a closed loop transfer function with respect to alpha. If somebody now adjusts, or if alpha moves, if that pole now moves around, it's now at minus alpha. If it moves a little bit, how does that impact this closed loop transfer function? How sensitive is our system to changes in alpha? Because if you now go to the stock room, Josie might give you some R's today, and Kurt might give you some different R's. Well, they may be the same R, but they may have a tolerance. So your alpha may be adjusted. You want your closed loop system to be behaving about the same no matter what R's are in the tolerance that's given to you. Now calculate the sensitivity S of the closed loop transfer function T with respect to alpha. But we can actually do that using the chain rule. We can break that up into 2 different sensitivity expressions. We could say the sensitivity of the closed loop transfer function with respect to a transfer function, G1, times the sensitivity of G1 with respect to alpha. And that's consistent with what you've learned in calculus, this chain rule. We can now apply that to this sensitivity expression. Let's now look at these different pieces. Let's find these 2 sensitivities on the right. First, suppose we start with the sensitivity of the closed loop transfer function T with respect to G sub 1. G1, remember, was that first block in our block diagram closed loop control system. By definition, this is the small change in T over T, these are all relative, over partial of G1 over G1. And if you now clean things up a little bit, push G1 upstairs, T keep it downstairs, you now have that times the partial of T with respect to G sub 1. And here is then the calculus that you need to perform. If we now look at the partial of T with respect to G sub 1, that's now the partial with respect to G1 of G1 G2 over 1 plus G1 G2. That was just T. That was our closed loop transfer function. And now just treat G1 like an X. You now have X times a constant over 1 plus X times a constant. And we want to differentiate that with respect to X. Take the partial. And we can apply our quotient rule if we want to that. We now have the derivative of the numerator to G1, which is just G2, times the denominator, minus the numerator times the derivative of the denominator with respect to G1. What's that? If If I differentiate 1 plus G1, G2 with respect to G1, that's just G2. That's my numerator, and then I have 1 plus G1, G2 quantity squared. The numerator actually cleans up a little bit. I have G1, G2, G2 appearing twice, once with a positive sign and once with a negative sign. That term cancels that term. And I'm simply left with, then, for the partial of t with respect to G1, will just be G2 over 1 plus G1, G2 quantity squared. That's just the right-hand piece in that sensitivity expression. I now need to scale that or multiply that by G1 over T. I found what I've highlighted. Now let me find the sensitivity. And this is still just the first piece in that two-piece process using the chain rule. But the sensitivity of T with respect to G1 is now G1 over T times partial of T with respect to G1. G1, and now T was G1, G2 over 1 plus G1, G2. And the partial of T with respect to G1 was G2 over 1 plus G1, G2 quantity squared. So clear where all of that came from? Now what can we do? Well, we can start cleaning that up. We have a G1 and a G1 that can cancel. We have a G sub 2 and a G sub 2 that can cancel. And I have one of these 1 plus G1s that I can cancel there. Leaves us with, then, the sensitivity of the closed loop transfer function with respect to one of those plants or one of those factors, k over s plus alpha, is now going to simply be 1 over 1 plus G1, G2. That's the left-hand side of that two-factored expression. Then we need to find the second piece. We just found this guy. We now want to find the second half, which is just taking G1 and finding its sensitivity with respect to alpha. By definition, that's the partial of G1 over G1 over partial of alpha over alpha. That's now alpha over G1, partial of G1 with respect to alpha. And remember, G1 is just this k over s plus alpha. We want to calculate that, partial of G1 with respect to alpha, given G1 having the structure k over s plus alpha. We now have that, which we could apply the chain rule to again if we wanted to. That's the denominator times the derivative of the numerator with respect to alpha. What's that going to be? Partial of k with respect to alpha. K is a constant. 0 minus the numerator times the derivative of the denominator with respect to alpha. 1. Now we're doing binary, 0 and 1. This is now over s plus alpha squared, which now gives us minus k over s plus alpha squared. But that's just the one part of this entire S sensitivity of G1 with respect to alpha, we now need to scale that by alpha over G1 times the partial of G1 with respect to alpha, so that we now have alpha over K over S plus alpha times minus K over S plus alpha squared. Which, if we clean up a little bit, the K's go away. One of those S plus alpha factors goes away, and we're left with minus alpha over S plus alpha. And now we're done. Now we can find the sensitivity of T, the closed loop transfer function with respect to alpha, is the sensitivity of T with respect to G1 times the sensitivity of G1 with respect to alpha. The first piece was 1 over 1 plus G1 G2. The second piece was minus alpha over S plus alpha. And if we put all of those pieces together, cleaning up the G1 and G2, the G1 times G2 is just K over S plus alpha over S plus 1. One of those terms gets canceled by the S plus alpha. We slide an S plus alpha over where the 1 was. We have the other S plus 1 coming upstairs, ending up with alpha minus alpha times S plus 1 over S plus alpha S plus 1 plus K. Do you see the Bode plot for that? Well, maybe it's not so clean until you put in a specific value of alpha. But if you have a specific value of alpha, then you have a quadratic or a second order denominator. You have two poles, and you have a 0 in the numerator. Depending on where those two poles are, what's the high frequency behavior of this sensitivity expression? At high frequencies, what's the magnitude of this sensitivity doing? It's what? It's going down, isn't it? Because you have a first order numerator and a second order denominator. And at high frequencies, you're going to have an S over S squared type behavior. You have a 1 over S. And having a 1 over S is giving you this 20 dB per decade drop at high frequencies. And depending on alpha, what's happening at low frequencies? At DC, what's happening? Now, if somebody changed alpha at DC, you would say, oh, if I had any DC errors, now this is how alpha is going to impact that DC error. For example, what's happening at DC? Is it well behaved at DC? How do you find DC? Not the District of Columbia, but you plug in 04S. Doing that, you have minus alpha upstairs. That's okay. Really, you're more concerned with what's happening downstairs, because that might go to 0 and then it would be infinite, which sometimes you want an infinite gain in your open loop dynamics. But here you just have alpha plus K. So you have some bounded DC gain, and then it's going to roll off, and what happens in between, you have a 0 and you have a couple of poles that break. But you have this concept of what's happening to the sensitivity of this expression as a function of frequency, or I hope you do. If you don't, go home and think about the Bode plot. Let's look at another way of actually finding this expression, or calculating the sensitivity of a transfer function with respect to a parameter. And if you just are now waking up, or if you wake up after this, you can look on page 241 of the textbook for this other expression. What we have is the sensitivity of t with respect to alpha, but we said we could write that as the partial of the natural log of t over the partial of the natural log of alpha. Now let's parameterize t, the transfer function that we're interested in, as having a ratio of a numerator over a denominator, an n over a d. Those are, let's say, functions of s, polynomials of s. We could then say this is the partial of ln of n over d over partial ln of alpha. Now we get to play with what we learned in math class, the properties of logarithms. The logarithm of a quotient is, now we can just subtract those two values, can't we? We can take the natural log of the numerator minus the natural log of the denominator, and now we've split our sensitivity into the sum of two sensitivities. We can now write that as the partial of the natural log of n over partial natural log of alpha minus partial natural log of d over partial natural log of alpha. Which means that this sensitivity of t with respect to alpha, we could actually write as the sensitivity of our numerator with respect to alpha. That's what that first expression is, minus the sensitivity of our denominator with respect to alpha. That looks so nice, let's just use it. Let's use it on this previous example that we had. Previous example, we had a transfer function t of s that was equal to k over s plus alpha, s plus 1 plus k. All we now need to do is identify the numerator and the denominator. The numerator is k. The denominator is now s plus alpha, s plus 1 plus k, and if we wanted to multiply that out, we now have s squared plus 1 plus alpha s plus alpha plus k. Or maybe I don't even want to write it that way. Maybe I want to write it as s times s plus 1. Since I'm going to be differentiating with respect to alpha, maybe I want to keep alpha sort of isolated. It's another way of writing the denominator polynomial. To find the final sensitivity, we need to just find the two pieces. We need to find the sensitivity of n with respect to alpha. That's alpha over n, partial of n with respect to alpha. Alpha over n, and what's the partial of k with respect to alpha? That piece was pretty easy, wasn't it? Now let's find the denominator's sensitivity. This is now alpha over d, partial of d with respect to alpha. So we now have alpha over d. And now what's the partial of that green, the bottom green, with respect to alpha? That's just s plus 1, isn't it? And this is now alpha s plus 1 over our denominator, which was s plus alpha, s plus 1 plus k. And what's our total derivative? I'm sorry, our total sensitivity. Our total sensitivity of the entire transfer function with respect to alpha was the sensitivity of the numerator with respect to alpha minus the sensitivity of our denominator with respect to alpha. The first one was 0. The second one we just calculated pretty easily. And that should look just like what we calculated before. Is that consistent? We had a minus alpha times s plus 1 over the denominator, which was s plus alpha times s plus 1 plus k. Questions on that? All right, I noticed that everybody seemed to light up when I said Bode plots. Let's look at this with respect to a Bode plot. Let's follow that a little bit further. Let's say that we now assign some numerical values. Suppose alpha is 3 and k is 5. If we do that, what happens to our denominator? We now have a specific closed-loop system. That's what the transfer function was. Our closed-loop transfer function was t of s equaling, remind me what that was, k over s plus alpha, s plus 1 plus k. So that now we have 5 over s plus 3, s plus 1 plus 5. Or this is now s squared plus 4s plus 3 plus 5. Is that right? So that t of s, we complete the square, that gives us s squared plus 4s plus 4. We have 8, so that gives us another 2, and this is now our closed-loop transfer function. So that our poles are where? They're staring at us in that factored form, aren't they? They're at minus 2 plus and minus j2. So we had closed-loop poles at s equal minus 2 plus and minus j2. What's the sensitivity of that transfer function with respect to alpha? That was this minus 3 s plus 1 over s plus alpha s plus 1 plus k, and we are evaluating that at alpha equal to 3. So that this is now minus 3 s plus 1 times the denominator that we just found. What's that look like in terms of a Bode plot? You now have complex poles, don't you? Oh man, we never did that in 320, or we always rotated those around to become real poles. Well, now we've raised it up a notch. We have to start to feel a little bit more comfortable with complex poles. But What's the natural frequency of your pole? And when I say that, what are you seeing in your mind when I say what's the natural frequency of a set of complex poles? What are you picturing? You should be picturing how far away those poles are from the origin, the hypotenuse. That's your natural frequency. In this case, your poles, if you wanted to sketch this in terms of a pole zero diagram, we have a zero where? Where is our zero? It's -1, isn't it? And our poles we calculated to be at -2 plus and minus J2. And here is our natural frequency. That's just square root of 2 times 2, or 2.8 roughly. And that's where our poles, we could sort of assume those are going to start entering into our frequency if we were sketching the Bode plot. If I now said, let's sketch that, we now have, if we just want the magnitude, we can forget about the minus sign. We want the magnitude. And what's this doing at DC? What's the magnitude at DC of this sensitivity expression? Now that I've erased it or scrolled above it. We plug in 0 for S and we have 3/8, don't we? So if we looked at the magnitude of this, we had 3 over in the numerator and we had 8. So now we're halfway between a quarter and a half. We're at 3/8. That's our DC value, our magnitude. And if we were sketching this as a Bode plot, you would take 20 times the log of that. That's going to be a negative number. So we're starting our Bode plot here at some value. Let's say this is now the magnitude of our sensitivity in dB. Now, what happens first in this Bode plot? Which singularity do we find first as we increase frequency omega? And if we go back to the way we've done this before, if you rotate those poles down and have them on the imaginary axis, I'm sorry, on the real axis, they're going to be to the left of that 0, aren't they? Since they're at 2.8 and the 0 is at 1. So what are you going to come to in frequency, the 0 or the poles first? The 0. And what happens to your Bode plot when you hit a 0? Upstairs, it goes up, doesn't it? You're breaking up and you're going up at 20 dB per decade. Then what happens? Then you hit 2.8 and 2 poles kick in. I'm doing this very rough, but now that 2 poles kick in, what happens to the slope of that magnitude response? Pardon? It goes down, and it really only goes down as fast as this one was going up. We were going up at plus 20. Now we introduce minus 40, but we do the algebraic sum of plus 20 and minus 40, and we get minus 20. So we're now going down at minus 20 for all frequencies after this omega sub n. So here is minus 20 dB per decade, and this is plus 20 dB per decade. And that's the shape of our sensitivity function as a function of frequency. And now if somebody said, how sensitive is your system, closed-loop transfer function, to changing alpha at omega equal 2, then you know that it's a little bit more than what it was at DC. We'll pick up with Chapter 5 material next time.